Hey guys, it's your host, Subhra. Welcome to your favorite channel, Subhra the Geek. So today we are in our second video of our mathematics series of linear algebra. So today we'll be learning about the recap and a few parts of vectors and vector spaces from the last video, and today we'll be learning about linear system of equations. So guys, this is a series. This is a set of or series which I have planned with along with one of my very good friends who is working in the industry as a core data scientist for past couple of years, Debayan, as you have already know him from past couple of videos. So guys, this is another addition to that series only. So, if you have any queries regarding any part of your journey, we have made an exclusive Discord server for that. The link is given below in the description box. So, please do join over there. I and Debayan will always be over there to help you out throughout your journey. And we'll try to answer all your questions as soon as you can. And if you're new to my channel, please subscribe to my channel. Please hit the bell notification icon beside it so that you get notified each and every time you post a new video and you stay updated with all the videos. And please like my videos, please share them with your friends, please share them with the community who needs this kind of stuff. So our aim is to make you guys get the job which Harvard Business School has classified as the sexiest job of 21st century. So guys, without further ado, we will start. So I am your host Subhra, and with me is,
This is Debayan.
let's start, shall we?
So hi, welcome back. In our previous video, we talked about what vectors and matrices were. Just for a recap, if you have not seen that video, right? So vectors are compact notations that we use to denote dimensions or aspects of an object, right? So if there is a physical quantity, if there is a mathematical quantity, space, time, vector, any kind of quantity, we would like to denote them in this notation that we see over here, and we denote each of its dimensions as numbers. So we can write 1, 2, 3 like this. So this one has 3 dimensions. It's a 3D vector, right? Matrices are collections of set of vectors. So a single matrix can contain one or more vectors in the column format. So this a matrix can have a vector 1. So this is your first vector in the first column. You can have another vector 2, 4, 6 in the second vector, the second column, and this is another vector 3, 6, 9. So this matrix consists of 3 vectors, each of which are 3 dimensional. So the dimension of this matrix would be 3 cross 3. This is the number of rows. This is the number of columns. Some of you might have noticed that a vector can be called a matrix if you consider that a vector is essentially a 3 cross 1 matrix, right? So this is the number of rows, the number of dimensions, which is 3, and this is the number of columns, which is 1. So when you write in notations, when you talk in notational format, each of them can be represented in the same way, which is used in square brackets, and you write your numbers in the columnar format. If there are the number of rows denotes how many vectors are there. So if there is one vector, that's essentially just a single vector. This vector, when you write it in this way, is what you'd call a column vector, right? So this is in a column vector because this is in a vertical format. There is also another kind of vector which is called a row vector, and you can see them written like this. So what's the difference between these two things? These may seem to contain the same numbers, or they might contain the same numbers, but they do not mean the same thing. Refer back to this definition over here. You can say that a single vector can be written as a 3 cross 1 matrix, right? If you go by that analogy, a column vector can be called a 3 cross 1 vector, sorry, matrix, right?
Yeah.
However, row vector is you denote it as a 1 cross 3 matrix. What this means is this is there are three vectors in it. It's 1, 2, and 3. These are individual vectors and they are one dimensional vectors. So they just contain one single aspect, one single dimension. And if you stack them one after other, you have essentially a matrix. So this representation is technically a matrix, but you call them a row vector because it's just the horizontal version of the thing that you see over here. But these are, please remember, these are two different, completely different things, and they mean different things. So the last time we left off, we were talking about multiplications, right? So we're talking about how do we multiply or work with the multiplication operation in our vectors and matrices, right? So let's talk about it. There are two kinds of output that you can get when you multiply or work with multiplication operation in the vector space, right? And this is and you can sort of classify it like this. So you can have
Scalar output
a scalar output.
or a matrix output. And a matrix output, if I'm not wrong.
Yeah. So there are two ways. So you can have a scalar output or a matrix output. And please remember, by the same definition like we defined over here, a matrix can be a vector as well if you consider a single column vector as a 3 cross 1 or an n dimensional matrix, right? So it's a n cross 1 matrix. So it still falls under the same kind of language or vocab that we use in this framework, right? So when do we get a scalar output, right? So what do you mean by scalar? Scalar means a simple number, just a single number. There is no vectors, there is no matrices. We just get a single number, right? So what kind of, how do we multiply vectors such that we get a single number as an output, right? There's one way. It's called an operation is called a dot product operation, if you have heard of it, right? This is what it looks like. So the way that you get a scalar output from vectors and matrices is when you multiply a row vector with a column vector. Let me give you an example. Let's say a row vector is 1, 2, 3. This is a one-dimensional, consists of one-dimensional vectors. There are 3 of them, and a column vector can be 4, 5, 6. So this is a 3D vector, which is or a 3 cross 1 matrix, which has just one vector, which is 3-dimensional, and this one is 1 cross 3 matrix, which has one row, right? So there's only one dimension. So these are 1D vectors in essence, but there are 3 of them, right? And the way you multiply them is simply you multiply them, you pair them up in this fashion. You say 1 cross 4 plus 2 times 5 plus 3 plus 6, right? And you get an answer 4 plus 10 plus 18, which is equal to 20 to 32, right? The way that you sort of visualize this operation is, consider that you keep 1 2 3 as it is, right? You take this vector and you place it over top of here. Let's visualize this operation, right? visualize this operation. Keep it over here. What you're gonna do is you're gonna pass it and map it like this, right? So you're gonna multiply 4 and 1, 5 and 2, 6 and 3, and then you're gonna add them and you're gonna get 32, just like we did over here. So if you're more into remembering these things in terms of formula, so you sort of take this, multiply with this, take this, multiply with this, take this, multiply with this. If you're more of a visual learner, I would recommend that you put this matrix on top of this matrix, or this column vector over top of this row vector, and you map it element by element, and then you add the answer. You will get a scalar value, right? So that's your scalar output. Now when it comes to the other type, which is you can get a
Debayan, I have a
matrix.
question over here.
Mm-hmm.
So, can we multiply a vector with itself?
Yes, you can. Yes, you can. And let's take an example, right? So you
Yeah.
have
Can you
1,
show
2,
us one?
3.
Yeah.
Yeah.
Yeah, yeah, yeah.
Right. So this is a row vector, right? We can technically do an operation called transpose, right? And what you do is that sort of revert it. You sort of reverse it into the opposite format of it, which is a take a vertical position. You just keep everything as it is and transpose it. So your row becomes the column and your column becomes the row, right? So this is what it looks like. So the transpose of row vector 1, 2, 3 is a column vector 1, 2, 3, right? So when you perform this operation, right, you do the same thing, right? So let's look at it visually. You're gonna put 1, 2, 3 over here. You're gonna put this vector on top of this of the row vector. Let me color code it so we can see it, right? And you're gonna map it one by one. You get the answer 1 plus 4 plus 9, which is equal to 13.
14.
Right?
Debayan, 14, it would be equal to 14.
Okay, sorry about that.
No
So
issues.
14. Yeah, even I make mistakes, you know. So 14. So this is what you would call the self product, like a self dot product, right? So whenever you perform a dot product, you should always know that you're gonna get a scalar value that bit is confirmed. That's the output of a dot product. That's how we define a dot product. And your inputs has to be a row vector and a column vector in some form, right? We're going to talk about how, like, we can talk about more instances of this where you can get a scalar vector from matrices as well, but those generally tend to reduce into the same form that we discussed over here. It's just a row vector and a column vector. In the language that we use, that a vector can be a matrix with one dimension or one row or one column. That language sort of changes over there, but the operation still remains between a row vector and a column vector as always.
So, Debayan,
Let's
transpose as a notation, if I'm not wrong.
transpose is an operation, right? It's like what is called a unary operation, or you just require one thing to to operate it on. Just like when you say -5, right? So this is a number, it's a -5. So this is a unary operator. It just works on one value, right? So the same way, transpose is just a unary operator. And the way you show this, that if your vector is 1, 2, 3, right? You say it like this. You keep a t over here, or you may say it like this, or in some books you might find it like this, an apostrophe, right? So what this means is the same thing. You just write it in the, like, you just convert rows into columns and columns into rows. You just invert it, and this is your transpose of that vector. So if you now transpose this thing, the row vector, you should get back the original vector, right? So please remember, so when you do a transpose operation, like if you have to, what you do is just interchange the rows and columns. So if this is now in terms of dimensions, if this is a 3 cross 1, so this becomes a 1. So this becomes a 1 cross 3. And you transpose again, it becomes a 3 cross 1 again. Yeah. Let's now move into multiplying or finding places where we get a matrix output of some form. So in a matrix output, let's write a sample equation over here. Let's write it like this. So you have a matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Let's say we take a vector, we multiply with that with a vector. We call this, like 10, 11, 12, right? So how would you perform this multiplication, right? The first thing that you gotta check is whether the matrix is conformable, right? So which is you gotta check the number of you gotta check the dimensions of this matrix, which is 3 cross 3, 3 rows, 3 columns, and this one is 3 rows and 1 column effectively. That is a column vector, which is effectively a 3 cross 1 matrix, right? Two matrices can only be multiplied if the number of columns in the first matrix is equal to the number of rows in
Rows.
the second matrix, right? Why do we say this? Why do we make those two numbers only, right? Why do we compare those two numbers? Here's how it's gonna make it clear, right? Let me remove this. So the way it works is the same as before, like we saw with these two matrices, these two vectors, right? So you take, let me write
Debayan,
write
can
it
you
on.
zoom a bit?
Yeah.
Yeah.
So this is your matrix. You're gonna take this vector, the matrix, right? You're gonna place it on top of this one, just like before. Then we color code it again, right? What you're gonna do, same as before. You're gonna map it, this column. You're gonna multiply this. So earlier, there was only one thing to multiply, right? So you do the same. You do the same, right? So what you do over here is you multiply 10 with 1. You multiply 11 with 4. You multiply 12 with 7. And then you add them up. Just like we did over here. You multiply element wise, then you add them up, you will get a scalar value. You got this. You got a scalar value. But this one, because there are 3 rows now, this one sits as the first element of our answer. This answer will have the format 3 cross 1. Now you can see why the dimensions mattered, right? You can see that this one will map on to the number of columns over here, which should be equal to this. If these two are not equal, you cannot perform this operation. So the matrix is not defined. Multiplication doesn't make sense. You repeat the same with the second row as well. You multiply 10 with 2, 11 with 5, and 8 with 12. And then you add them. You'll get a scalar value again. And you're going to do the same. 3 into 10, plus 6 into 11, plus 9 into 12. So the vector that you will get is a 3 cross 1 vector or a matrix, right? And this is the answer to your matrix, to your multiplication operation over here, right? The next advanced step would be to multiply matrices with matrices. It's the same thing, we just repeat it another way, right? So if you have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, you have another matrix over here, let's say 10, 11, 12, 13, 14, 15, right? So how are we gonna multiply these things? So let's check the dimensions first. 3 cross 3, 3 cross 2. It maps. So you can now map this thing over here and do the same mapping. We're gonna do that right now. So this thing maps. So we know just from this that our effective answer should have the dimension 3 cross 2, right? So let's write it down. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're gonna take this one column vector, very similar to this one. We take one column vector, we're gonna position it out right over here. I'm gonna color code it, right? We're gonna match this. same as before. We're going to get an answer that will have a 3 cross 1 vector, right? We're going to multiply each of one of them. We will get an answer over here. We're going to get another answer over here. We're going to get another answer over here. So that's a 3 cross 1 vector. But we don't stop here like the previous step, because we have another column vector over here. We need to do that for that as well. So we do the same thing. We're going to now put 13 over here, 14 over here, 15 over here. Just going to transpose this whole thing on the top over here again, and we're going to map it. Let me color code it just for the sake. We're going to map it one by one. You will get scalar for every row. This is another 3 cross 1 vector, and you bunch them up into one matrix. So the answer will be essentially a 3 cross 2 matrix. I hope this process has been visually simple enough for you to sort of follow. Many books sort of do not sort of cater to these things. They just give you the raw formula, which is, I believe, a bit difficult to sort of remember and apply most of the times. And this is how I sort of learned to do this kind of operations very quickly, right? We're gonna now
Actually,
extend
this is a very good process. I also love this process, and actually, we also like I also learned like this. Remember the man we used to talk about this.
And let me share a clue. Where did we learn about this as well, right? We learned about this way of looking at matrices and vectors from Gilbert Strang. If you just Google up Gilbert Strang, like, he's the professor at MIT known for linear algebra. He's sort of like the brand ambassador for MATLAB software, and like, he's the guy you go to when you have any questions regarding linear algebra. He is the authoritative figure in my opinion on linear algebra. So please, do check him out. Do check out his books. Those are standard textbooks for linear algebra. So we're gonna quickly transition this. We're gonna use this same language, the same flow that we're having, and moving on to a very useful framework of systems called linear systems, right? So since now we have been working with matrices, we have been working with vectors, right? And which may or may not have outputs which are vectors or matrices, right? This form that you see over here, this form, that this is a matrix, is a vector, and this can be a matrix or a vector. Like, both of them are, in the sense, interoperable if you consider the dimensions properly, right? So if you consider them, this operation is very similar, or can be used to reproduce the systems of linear equations, a polynomial that you use, right? So what do I mean by that? So when you have an equation, right, ax plus by plus c is equal to some value d, right? And you have, like, many equations like this. I think in school, if you had something like this, you would be asked to sort of solve these equations. I think it's called simultaneous solving of equations, and you have many of these, and the teacher would ask you to sort of solve this simultaneously and find a solution that solves all of these equations by, say, one value of x, y, and x and y. There are two unknowns over here, x and y, right? This is what we call a linear system, because we can represent the same problem into a matrix form, which is much more compact and much more easier to write, right? So here's how we're gonna do this. We're gonna put x, y, and there's no operation over here. We're gonna put this as 1, right? It's just a identity operation. So we're just gonna put that as 1. So what we're gonna do is we're gonna put x, y, and 1 over here, right? And we're gonna put these values over here. If you remember this, if you sort of follow the logic from here, if we put this on top of over here and map it, right? So you should get a1x, b1y, c1 1. We sort of get back the original equation, right? So we're gonna continue doing this for the other equations as well. We're gonna put a2, b2, C2, we're gonna put all of them. We're gonna put them all over here. Where do the D variables go? They're gonna go over here. Why? Because this is the answer. Just like over here, this is the expression, right? So how do you sort of transform this, and where do we get the advantage from? First of all, we are compacting. We're sort of representing the whole system of problems into a compact representation, a matrix representation, right? And we're gonna the whole equation sort of sits right over here. If we sort of do the same visualization over here, we get the equation back, and correspondingly in the same row we have the answer. This is very good for programming. This is very good for memory representation when you're working with, when you're storing this and doing this operation in programs, in computer programs, right? So this is what we call a linear system of equations, and you'd see that this the number of rows over here. These are the number of equations you have. Let's say those are m, right? The number of columns that we have is the number of variables or number of coefficients that you might have. Those are called n, right? So it's an m cross n vector. The number of unknown variables will follow that pattern, which is n cross 1. These two has to match. In case I'm being very unclear about this is n cross 1, so these two has to match. That makes sense, right? So there are three variables, so it should match over here, and this one should be an n cross 1 solution.
M cross
An
1.
Yeah, so sorry, an m cross 1 answer. Why? Because these two match. The remaining variables form the dimensions of the resultant vector. You can see how the matrix operations can be used to define the vocabulary for solving linear systems or multiple linear systems in one go. This is how we represent that information. And if I'm not being sort of like a reductionist in this thing, right? Let me show you how this briefly. Let me show you briefly how this connects to machine learning or data science, right? So this notation is what we call in linear algebra as ax equal to b, where x vector, that n cross 1 vector, will consist of all the unknowns about the problem. This one will contain the coefficients or the values that you set before each one of those variables, like you saw over here. And b will contain the answers, right? This is how linear algebra presents this form of solving linear systems, ax equal to b, right? In machine learning, it's the same thing, but we have different way of representing the language. The language is, this is the data. Let me remove this. This is the data output. This is what you want to predict. This is your answer. This is what you want the so-called model to learn, right? This is the answer that you want to learn. So this is the data output, and this is always going to be a vector like this, some answer vector, right? This is the variables or the columns in your data sets, right? So if you have a data set, if you take an Excel sheet or something, the column names are your variables, and the seat in X, you can see how it should be an n minus 1 vector.
N cross 1.
Because n cross 1 vector just sits there, which represents all your unknowns, all your variables that you have about the system, what you can and cannot know about the system, about your problem. A is your collected input vectors, input data, right? This is your input data, and this is what you collect, what companies collect, right? So you hear about this deep learning processes, these machine learning processes. The companies, they are mining huge amounts of data, right? So when they say they mine or collect huge amounts of data, this is what they mean. They mean that they're collecting this, and if possible, they're collecting the output as well, right? So if the majority of the problem lies in finding A and the output, so A and B. If they're B, it becomes a very simple problem. So you have the answers, you can train your model to sort of map your answers to that. So that's called like if you're going a bit off topic, that's called supervised learning. But if you don't have B, then it's called unsupervised learning, and there are other kinds of learning as well. We're going to go into this later on. But A is what you should be concerned about. A is the data set that you collect. A is where all the money lies. A is where the insight lies. We want to talk about now the insight, how did machine learning connect this form over there? How did we learn to use that form in such a field which has so much of an impact in every day of our lives, right? There's a mentality, there's a philosophy behind this equation. There's a modus operandi, as one may call it, behind how one can approach solving a real life problem, right? So whenever we start talking about solving problems, right? Solving problems mathematically, solving problems using uh, numerically. I think that's what the term is. Solving problems numerically using data. That's the key part. Whenever you talk about solving problems using data, right? You always start with a very simple understanding of what we can do, what we want to do, right? That simple understanding is generally, I believe, is always a linear model, right? So we always start with a simple model. Simple as in you just add things and you get an answer. That's the simplest anyone can think of, right? So you just say, I want to add my variables x plus y plus z and so on and so forth, and you get an answer. This is my model. This is how I'm gonna solve the problem. This is how I'm gonna represent the problem. I'm gonna approximate the problem into something that I can understand, I can work with, and I can interpret. I can say it's a summation. The answer is a summation of all these factors, of all these variables, of all these parameters. You see the language that we use here? It's sort of an addition of this. This is what you call a linear combination, right? So a linear combination of variables, factors, parameters, influences. The synonyms can be, it sort of follows the same line of synonyms, right? So any linear model, like we have seen before, can be expressed in this form. Why? Because any linear model or set of linear models can be approximated, the parameters of these variables sort of go into A, like we saw before. These are contain all the parameters. The parameters go over here in every row. The variables that we have in the problem that we sort of approximated using the linear model goes over here. So you have all your variables, all your unknowns into one column x, and then you have the answer, the expected answer that you want in every column. This is the answer. So if you can reduce your problems into this form, into this linear form, you can now use the properties of linear algebra, of vector spaces, addition, subtraction, multiplication, to solve the problem, and you will get an answer very quick. Now there are various ways of solving this equation, this ax equal to b. One of them being inverse products, but we're going to talk about them in a next video. We're going to talk about them in an upcoming video. The philosophy that I want you guys to sort of take away from that, one of the basic things that you can do in solving any kind of machine learning data science problem is to put them in a linear format. Think of what are the parameters that I want to influence. What are your influences? For lack of term. What are the influencer variables? What are the factors? What are the parameters that you have? Which one affect your output? Right? You say you add them up in some weighted format. You say this one has some weight, one has, if I say 100% weight, 100% as a weight, right? So this one has 0.2% or 20% weight, this one has 0.5% weight, and this one has, let's say, 3% weight, and you want to add them up in that in a particular combination, and you get an answer. This is how you solve, you sort of represent your problem in a very basic kind of way, and this is a linear model. And whenever linear models are there, you always have this form. Whenever you have this form, you can always use linear approximation, linear solutions, vector spaces to solve those.
So, as per today's lecture, what we understood is dot product and scalar product. Then we understood how we can visualize them and how what is the power of visualization and how the power of visualization actually helps us. Then we really understood how can we and what is the need of actually reducing a very large problem into linear spaces. And if we can reduce it to linear spaces, then we can solve our problems very easily, because linear things can be easily visualized, easily seen, easily understood by us. That's it. And we will be trying to focus on this, like how to bring complex things into linear things in our future series, if I'm not wrong, Debayan.
Yeah, we're gonna expand on this idea,
Yeah.
but this remains a core thing. If you understand this, you're set. You definitely you will be comfortable in the upcoming videos, the content we're gonna push in.
Yeah. So, guys, that's all for the day. Thank you for staying with us for so long and understanding all this concept which my friend Debayan has explained to you from his understanding of the industry. So we'll be meeting next week at the same time on your favorite channel, Subhra the Geek. I am your host Subhra, and with me is
Debayan.
signing off. Bye bye.